Which one?
The Boston State Scholarship.
Yeah, the very top, bottom. I mean.
Bottom?
Yeah. No. Okay. Below that, that's it.
There we go.
I thought you had already done it.
I don't have it printed out or filled out yet.
Oh, I see.
I got it turned in when I...
Oh, I see. Got it. Okay. I thought you were waiting on me. Okay. Now I can wait on you. I'm sorry. Okay. Okay. We are recording. I did want to make this one other small announcement. I think I made it before, but just in case I missed. In fact, I probably have my dates wrong. I thought the first mini-term ended last week. Second mini-term started this week. Actually, the first mini-term ended Monday, day before yesterday of this week. I didn't know that. I had a Tuesday, Thursday class. I knew my last day was Thursday, so I assumed they were already through, but they aren't. Okay, they are now. So that means that if I have to do that, whatever they call it, midterm progress report, I need it. They probably give me through next Monday to get it done. So you sort of luck out with a weekend, okay, another weekend, if you still need to finish a test or a paper. So please try to get me something. A couple of you have today already, but try to get me something before by next Monday, okay? The other thing is my office hours changed ever so slightly. First mini-term, I had a physical science class starting at 12:30 on Tuesday, Thursday. This term, it starts at 1:15. So that means my office hours on Tuesday, Thursday go from 10:45 to 1:15 rather than 10:45 to 12:30 like they did last term. It's only 45 more minutes, but they sure are going to be helpful for me. But if you need to see me Tuesday, Thursdays, they are there. All right, let's get set up with the current slide. And I want to know first, do you have any questions? Now, I don't know why it's there. Okay. Let me even turn on the projector for you. There is one other little thing. We're going to start with Bernoulli's equation today. But what I wanted to do, I meant to say this last time, and I kept thinking about it but never getting it said. It dawned on me when I was driving home or after I was home or sometime. I said, I never said that, did I? Let's go back to the concept of homogeneous differential equations. Okay. Now, for those who may have had or be taking now linear algebra, or if you remember back when we did systems of equations, if you ever had a system of equation that all of the, x plus y plus z is equal to 0. 7x plus 4y minus 3z is equal to 0. That everything over here, all your equations or whatever, all your constants were zeros. We call that a homogeneous system of equations. That was the first time I ran into the concept of homogeneous. Earlier in the book, and they made a mention somewhere back when we were doing this, it's not the same homogeneous we talked about before. When we're talking about a linear equation, that, remember that special form, dy dx is equal to p of x, y, plus p of x, y, I always say equal. dy dx plus p of x, y equal f of x. That's just a regular linear differential equation. If, however, the f of x was 0, we called it a homogeneous linear differential equation, right? That's what we called it back then, when it was equal to 0, just like that system of equations. Basically what that means is that there's always at least one solution to every one of those, and that's y is equal to 0, or x, y, your 0 vector is a solution. May not be the only solution, but it always is a solution. Now, that's not what these homogeneous equations were. You saw that, okay? What makes these homogeneous, if you look at every one of them, well, we only had, on page 71, that first example, f of xy is equal to x cubed plus y cubed. That was homogeneous, okay? The next one we looked at was x squared plus y squared dx plus x squared minus xy dy, that's equal to 0. Now, that's not homogeneous because it's equal to 0. It's homogeneous because the degree of every term is the same. If you look at that, x squared plus y squared, both of those have the same degree. dx, that's there. Those are both degree 2. The next one, though, plus x squared minus xy. Well, x squared is degree 2, x is degree 1, y is degree 1, so those add to be 2. So every term is equal to, the degree is the same, okay? And the x squared plus y squared, x cubed plus y cubed. That's homogeneous. That's what homogeneous means in this case, that every term has the same degree. Now, why couldn't they have said that rather than saying that f of tx, ty is t cubed, or t to the alpha, f of xy? Yeah, that's saying the same thing, but man, why make it so complicated? Just say it, and I happen to think, why didn't I say that? All right, now let's move to Bernoulli's equation. Here's a differential equation, dy dx. Boy, that looks good, doesn't it? Okay. dy dx plus p of xy, boy, this looks familiar, doesn't it? Is equal to f of x. If we stopped right there, we say, yeah, we know how to do that. That's one that we do by integrating factor, right? E to the px dx, remember that? Except this one doesn't stop there. It has f of x, y to the n. Uh-oh. Where n is any real number. This is now called Bernoulli's equation. Let me make sure I spell it right. Bernoulli's equation. Now, the trouble is, I don't know which Bernoulli. There was a whole family of great mathematicians and physicists named Bernoulli. They were mostly kin. I mean, there were 2 brothers, and one brother had at least 2 sons, and they were always competing against each other, and they weren't very functional family. They were pretty dysfunctional. They were at each other's throats sometime, other times supporting each other. Quite a family of mathematicians. I don't know which one this is named after. One of the fathers, one of the sons, huh? Okay, yeah. Which time? This time or earlier term? This term, yeah. I thought I had seen one. Was that to do with this equation, or was that to do with just in general? Okay. So you think it was Jacob, okay? I think his brother's name was Johann, and then the sons of one of them, I don't remember their names. It seems like one started with S. Okay. And I think some of them had more than one son, and they were all really good mathematicians. Swiss, I believe, weren't they? Okay. Yeah, I believe they were Swiss. Okay. So where n is any real number, that's Bernoulli's equation. Now, how did that happen? Now, if the n happens to be 0 here, y to the 0 is? Y to the 0 is? Y to the 0 is? 1. Anything to the 0th power, except 0, that's not defined, is 1. Okay? So this would be 1. Then you would have a linear equation that we can solve by the integrating factor. Okay? But for any 0 other than, any n other than 1, and of course, for n equal 0, you have that one. If n is equal to 1, though, okay, then this is y. Then you can divide both sides of the equation by y, okay, and the y's disappear, and then you just have a simple separation of variables, okay? Just move add the px over here, multiply the, yeah, you can separate by variables. So n equals 0 gives you the old linear equation that you use integrating factor, n equal 1, that gives you separation of variable problem. That's pretty simple. But if n is anything other than 0 or 1, then this is what we call Bernoulli's equation. Okay? Now, what do we do with those? For any n other than 0 or 1. Now, remember now here, n is any real numbers. Quite often we think of n as being an integer. Okay? Or sometimes even positive integers. That's not the case here. N is any real number, not just integers. Any real number, except 0 and 1. 0 and 1 give special cases, but if there's anything other than that, then here's the substitution you use. U is equal to y to the 1 minus n. Whoa, okay? Now, and if you use that substitution, you'll get it into a linear equation. Now, okay. And basically, if you think about what you've done then, you divided both sides by y to the n. And then you had it looked like dy dx plus p of x times y to the 1 minus n. Y up here, it would be 1, I'm sorry, it would have been, yeah, 1 minus n equal f of x. Huh? Where's what? That's a plus. It's, my pen just didn't write well. Okay? Same thing as before. So that should help you remember what the substitution should be. Okay? So, let's do it. Okay? I'm going to start from scratch, so I'm going to erase all this. And here's your problem. X dy dx plus y equal x squared y squared. Okay? Now, that doesn't look like our prototype at all, does it? I mean, sort of close, but not quite. Okay? What would be the first thing you would do here? Notice Bernoulli's equation doesn't have anything in front of the dy dx. So the first thing you better divide by x. Okay? So let's do that. Divide every term by x. Okay? These go away. One of those goes away. So now we have dy dx plus 1 over x y. That's looking more like Bernoulli's equation, is equal to xy squared. Okay. Now, what I suggest that you do next, just because it helps me remember, and they don't do this, so you don't have to do this, but I just go on and divide by the y squared. Okay? No, sorry. No, let's not do that, because then you would be messing up the first term as well. So forget that. Okay. Just use it to remind yourself what the thing is. Okay. The substitution we'll do is let u equal, and what did we say it would be? Y to the 1 minus, in this case, 2. So that would be y to the minus 1, which is 1 over y. There's your substitution. Okay? Now, if that's the case, du dy would be what? Let's use this form to take our derivative. What would that be then? Okay. Okay, I was starting to do it this way. Okay. The thing is, they've done things that looks like to me a little on the backward side. Okay. They're doing dy du rather than du dy. So let's not do it the way I was going to suggest. Okay. It seemed like to me that would make more sense, but they're doing it this way, so let's follow through with what they're doing. So there's your substitution. Let u equal y to the minus 1 or 1 over y. Okay. Now, here's what they're doing. This dy dx that you have here, they're breaking down into dy du dx. Fine. It's just not intuitively obvious where you have u as a function of x. It looks like u is a function of y. But, of course, y is a function of x, so ultimately u has to be a function of x too, but that just makes it look a little strange. So, anyway, we're going to do that, okay? Now, so that's your dy dx becomes that, okay? That is the left-hand side, okay? But if you look at this, if u is equal to y to the minus 1, that means y is equal to u to the minus 1 as well, right? Because if you multiply both sides by y here, and then divide by u, you get y is equal to 1 over u. So that would be this. And since we want dy du, we take the derivative of that, which seems backward to me, but we'll do it. Dy du then would be what? Same thing we just did, or we're starting to do it. What would that be? Minus u to the minus 2, right? Minus 1 u to the minus 2, right? So this becomes, the dy du becomes minus u to the minus 2 du dx. All right. Now, we put that back into our equation, okay? So this becomes minus u to the minus 2 du dx, that's what this is, plus 1 over x, but remember what our y is? Y is u to the minus 1, so that's 1 over ux, or xu, or whatever, okay? Okay? Equal to x, which is already there, and if y is equal to u to the minus 1, y squared would be u to the minus 2, right? So that would be u to the minus 2. Okay. Now, I'm a little tired of having some u's upstairs and some u's downstairs, some with minus, some with something else. So let's multiply through everything by a minus u to the minus 2. Okay? No, divide is what it means. Multiply by minus u squared. Minus u squared by every term here. minus u squared minus u squared minus u squared. Okay? So this will go away. Okay? That'd be plus u to the 0. So you have du dx, that's looking better, plus, and actually it's going to be a minus now, isn't it? Okay? Minus, and you, okay, the minus went over there. I can't get my pen back. Okay, this u went into one of those, so it's minus u over x, right? Okay, is equal to, and here these went out, but you still left a minus x. Goodness gracious, that's a pain in the neck. All right, and that's what they got as a differential equation, okay? Du dx minus 1 over x, u is equal to minus x. Now that has been changed back into a one that we can use an integrating factor. Okay, right? Remember, du dx, why is my pen not writing? Okay, there it is. Minus 1 over x, u is equal to minus x. Okay? Now, remember, this was our p of x, and this was f of x. And that's just like, this is a pain, that's just like your integrating factor problems. And what was the first step in that one? Now, I need more room. And I'm going to start erasing some stuff soon, and I'll probably screw some stuff up. But let's carry on here. What's our first step with this form? Yeah, you do the integrate 1 over x. Now really it's a minus 1 over x, okay, dx. Remember that? What does that give us? ln, minus ln of x. And what do we do with that? Well, one thing I'm going to do, I'm going to write it as ln of x to the minus 1. I swear this is such a pain. Okay, and then what do we do with it? That was the argument of the e function. So then we do e to the ln of x to the minus 1. And what does a e to the log do? They undo each other. Those are inverse functions of each other. So basically you got, this is 1 over x. I don't know if that's the form I wanted in, but that's what it's going to use. And what do we do with that? We multiplied that by every term on all three sides, right? So that's where I need to have more room. So I think I'll go up here for now. Okay? So I'm going to multiply that by here. So you get 1 over x du dx, okay, minus 1 over x squared, because you already had 1 there, u, and that was equal to, and when you multiply minus x by 1 over x, you're left with a minus 1, which is not a bad thing to have, is it? Okay. Now I'm going to start erasing some stuff, and I bet you I'll erase something that I need, but less for now, hope that I don't. Okay? The eraser is really, really slow. Okay? Really, really, really slow. I swear. I've never seen it this bad. Okay, I don't recall anyway. All right, I think I'll erase this too. I want to leave that line there because we're going to need it to come back to. I hope I won't need this one. I doubt if I'm going to need that other, but let's leave it for now. All right, let's get the pen back. Now, remember what we did before? We noted that this was a perfect, it was a product rule type thing. This is D by 1 over X times U. That's what we think it is. Okay? Let's see if that's true. That would be 1 over X du dx, that would be that part. Plus U times, and this is X to the minus 1, so that would be minus X to the minus 2, that's exactly what we've got there. So they'd have that is equal to minus dx, minus 1 dx. Notice what I did was, rather write that as d by dx, I put the dx on the other side. That's pretty easy to integrate, right? Integrate this, integrate that. What does this give you? Integrate a derivative, you get, they undo each other. These are operations, not functions, but they still undo each other. That gives you u over x is equal to minus x. And here we'll put in our plus c. Okay? Now, what was u? 1 over y. So what we have now is 1 over xy is equal to minus x plus c. Now, can you separate out the y? I think so. Let's reciprocate both sides. Make this xy is equal to 1 over minus x plus c. Now, I may not like the c with that. I may want to go back and change that somehow, and then divide both sides by x. Okay. So we have y is equal to, y is equal to something. It's like 1 over negative x squared. Goodness gracious. Minus x, plus xc. Okay. Or something like that. Now, they probably put it in a slightly different form. No, they leave it in exactly that form, or very close to it. Y is equal to 1 over minus x squared plus cx. That's exactly how they leave it. 1 over minus x squared plus cx. Why the pen is so slow in writing, I don't know. That's exactly how they leave it. Okay? Now, note that we have not obtained the general solution of the original nonlinear differential equation in example 2. We haven't. Since y equals 0 is a singular solution of the equation. Now, what they're saying is, look back at the original equation. X dy dx plus y equal x squared y squared. Right? That was our original solution. Forget about those x's I divided by. Okay? Well, looking at that, y equals 0 certainly is a solution because y is 0. Oh, yeah. And y is 0, and dy dx would be 0. So 0 plus 0 is 0. That's certainly a solution, but this wouldn't give you y equals 0 ever. Okay? So that is another solution that's not included in this one. Okay, so we know we have y equals 0. The rest of the solutions are in this form. Okay. Now, That was Bernoulli's equation. Any questions on that before I erase the screen? Okay, they gave you a very simple one. I guarantee you that the test bank will probably give you something a little more complicated. Don't you think? I bet so. Okay. Just because they like you that much. Okay. So now let's look at reduction to separation of variables. What if we had this? dy dx is equal to some f of ax plus by plus c. What a strange form. Okay? But let's say we had it in that form. Okay. Now, we haven't seen anything that quite looked like that yet, have we? So what they do is say, let's let u be that stuff in the parentheses. It's usually what we did when you did a substitution, didn't you? You take the most complicated part and let that be u, okay? And that's what we're going to do. So let's try that. Let u equal ax plus by plus c, okay? Now, it says it can always be reduced to an equation with separable variables by means of that substitution, as long as b is not 0, okay? Now, they just let it hang there. I have some real problems with this because u is now a function both of x and of y. So are you going to use partial derivatives there or what? Okay? Or sort of something like implicit differentiation. They're not really clear. So let's see if their example is going to give us any hints. And since we may need the whole page, I'll go on and erase all this. Just remember that's what they're suggesting. So here's their thing. dy dx is equal to, okay, minus 2x plus y squared minus 7. Okay? Now this is a initial value problem. Y of 0 is equal to 0. So even though we may wind up with a constant of integration or something like that, we should be able to evaluate what that constant is using that initial condition. Okay, don't sweat it yet. Now, what they say to do is not quite what I said them saying to do before, okay? But if you look at this, the thing that has all your variables in it is that thing right there. So that is going to be your u. Not with the square, the thing with just the variables. And preferably in linear form, which is what we've got here. That is a minus, yeah. Okay? So our substitution would be let u equal negative 2x plus y. That's all. The square is going to be part of the function, and then the function of this thing is going to be u squared minus 7. That's going to be the function, okay? But that's our substitution. Now, notice we're not going to mess around with our initial condition and try to change that to the u's yet. We're going to let that be for now. Okay, but let's do what they suggest. The next thing we do is then du dx is equal to, if u is that, what would that be? If u is that, what is du? Second, minus 2 plus dy dx. That's what we got to do because you got two variables there. Okay? Now, somehow it doesn't look like this has really helped us some because we still got a dy dx in there. Okay? But let's see what happens if we plug that in. But do this one step. Add 2 to both sides. And you got dy dx is equal to du dx plus 2, right? Hey, we can plug that in here. So instead of dy dx, we put du dx plus 2 is equal to u squared, remember that u squared, minus 7. All right, real easy to subtract 2 from both sides, isn't it? So now you got du dx, it's an ugly d, okay, is equal to u squared minus 9. You're right. Okay? And I don't see any x's in there. So let's separate variables and have du over u squared minus 9, so 9, is equal to dx. Got it? Integrate both sides. Uh-oh, how do we integrate that first? Anyone remember? Say again? No, that won't work because you have to have a 2u somewhere up there. So it can't be a substitution. Hint, this thing's factorable, right? U what? Plus 3 times u minus 3. Does that give you a hint? What? What technique would you use? Partial fractions. Very good. Okay, how does that go? Okay. You hope this thing is going to equal, not with the integral, we'll come back and do the integral later, will equal some a over x plus 3 plus some b over x minus 3, right? Partial fractions. And we hope that this thing, 1 over x u plus 3 times u minus 3 is equal to that. So what are we going to do now? Pardon me? No, Picky. Okay, yeah, it's u's. Sorry about that. Okay. When I think partial fractions, I go back to x's. Let me make these look prettier. Not much, but a little bit. Okay. Okay. That's a u. This is a u. There's a u, and there's a u. Okay. What do we do to solve that? Multiply by that denominator. Over here, I'm writing u, x's again. U plus 3 times u minus 3. Multiply this by u plus 3 times u minus 3. Multiply this by u plus 3 times u minus 3. Okay? Over here, everything goes out and you are left with 1. And that's equal to, here the u plus 3's go out, a times u minus 3 plus b, and here the u minus 3's go out and left with u plus 3. Okay, now we use a silly little trick here, which I find almost offensive, but it works. What is that? Remember what we did then? Okay, actually, You can do it that way. But the easier way is say, well, let's let u be 3. Now, to me, why I found that really objectionable, you can't be 3 because then you'd be dividing by 3 here and here and here. But they say let u be 3 and see what happens. So when we say let u equal 3, you have 1 is equal to, here, that goes to 0. And you have b times, if u is 3, that would be 4b, right? So b is equal to 1 over 4, right? Huh? If u is equal to 3, this goes to 0, and you have, oh, 6. I'm sorry, where did that 4 come from? Well, the eraser didn't show up. Okay, there it is. Okay. 6, okay. Duh. Okay. 6. So b is equal to 1/6. Okay? And guess what we'll try next? Let u equal -3. You still got a 1 here, and then this will be minus 6a, and this will be 0, okay? So then a is equal to -1/6, okay? So if we go back up here and integrate that, this integral here, I'm going to try to put it here, will be -1/6 the integral of, make sure I get it, yeah, the a is u plus 3, du over u plus 3 plus 1/6 the integral of du over u minus 3. Okay? I think we can integrate both of those, can't we? What would that be? Okay. -1/6, what were you saying? Natural log u plus 3 plus 1/6 times the natural log of u minus 3. And when you integrate that side, you just get an x. And we can say plus c if you want to. Or we can fiddle around with it for a while and get it to say something else. I need more room. So if it's all right with you, I'm going to erase. I don't want to erase that, but I will erase this. Okay, I think I can easily erase this and that. Okay, believe I can erase this. I sure hope so, because I just did. I'll leave that maybe for now. I don't think I need these anymore. I think I've already used them. So this. And I probably don't need those either, because I've got my answer. So I'll erase those, making some more room on the page. Now the eraser's doing much better. Earlier it was just rotten. Okay. I don't think I need this anymore. Okay. Yes, I'll just leave that just because I've got enough room now for a while. Okay. Let's play around with this a little bit. This is the same as the log of u plus 3 to the minus 1/6, and this is the plus the log of u minus 3 to the positive 1/6. where do I want the C? I don't know for sure, so let's just keep going. And then you can combine these, and actually, let's leave that minus sign out in front. I should have done that. And that would have had us the log of u minus 3 over u plus 3 to the 1/6. And you might need absolute value signs, I don't know, okay? And that's equal to x plus c. Let's plug in, wait, whoa. We got to get rid of the u's and get back to what we started with. So this will be the log, natural log of a minus 2x plus y over a, plus 3. Minus 3. Yeah. Minus 3 over minus 2x plus y plus 3 to the 1/6 power is equal to x plus c. Okay? Now let's plug in x equals 0. So that's going to give me a c over here. And what do we have here? That's the log of, when x is 0, y is 0, that would be minus 3 over plus 3 to the 1/6. Well, that's a minus, ooh, boy. Let's put the absolute values back in there. Okay, that would be 1. Okay, and 1 to the 1/6 would be 1. So it looks like c is equal to 1. Now, no, log of 1 is 0. Sorry about that. Okay, that would be 1, but then we're doing the log of 1 would be 0. So c is equal to 0, I think. Now, I've done a lot of sleight of hand here, and let's see if we've gotten way, way, way off base. Okay? Okay, they had exactly what we did in a sense. No, they actually get C to be minus 1 like I was starting to get, but they did a different way, and you see, it's kind of a mystery, okay, when you get rid of the C and when you don't, okay? So they were okay. We were on the same page up until here, okay? So let's get rid of this. We're going to redo this a little bit, okay? In fact, I'm going to take out the 1/6 here and move it in front. Where's my, there it is, okay. 1/6 times that log is equal, and they put x plus c1. Now they're going to do that for a reason, okay? What they're going to do now is multiply both sides of the, multiply both sides of the equation by 6. And that gave them a log, and are they keeping the parentheses? They don't. Yes, they do. No. They keep them for a bit here, okay? Of u minus 3 over u plus 3 is equal to 6x plus 6 c1, right? Looks a little strange. Now they take the log of both sides. And that gives them u to the minus 3 over u to the plus 3 Now they forget about the absolute values because you can take the e of a negative number. Okay, so or e is always positive, so that's going to be a positive number. And rather than doing e to the this, they change that and make it, this would be e to the 6x times e to the 6c1. But e to the 6c1 is just some constant. And they change that to the c. That'd be c e to the 6x. Okay? Now, what I was doing was plugging in the x equal minus 2, u equal minus 2x plus y in there. They're not doing that. They're solving for u first, which seems an awful suggestion, but let's do it. Multiply both sides of this equation by u plus 3. Okay? Now, I think I'm going to need more room, so I'm going to erase some more. Let's erase this down here, hoping I will not need it, because I think I've already undone that. Okay, and we've already done all that. Okay. Okay. All right. So, let me rewrite this as u minus 3 is equal to c e to the 6x u plus 3c e to the 6x. Okay? Now, I want this term over here. I'm going to add 3 to both sides and subtract the c e to the 6x u from both sides. Okay? Plus 3 here and a minus c e to the 6x here. U. Okay? What that turns out being, these go away, those go away. Okay? So your left-hand side becomes u times 1 minus c e to the 6x. Okay, because I factored out the u. That went away. Okay, on the right-hand side, those went away, and we have 3 times 1 plus c e to the 6x. Okay? Now we'll divide both sides by 1 minus c e to the 6x. Okay, so those go away. Now that u is what your minus 2x plus y is equal to. Okay. Yay. All right. If you solve that for y, then just add 2x here. Okay. And there you solve for y. Okay? I think it looks the same. I just got the 2x at the back rather than front. Now we're going to use our initial condition. Y of 0 is equal to 0. So that's going to be 0 on the left-hand side, that's the y, is equal to 3 times 1 plus c. Now e to the 0 is 1. So 1 plus c here over 1 minus it better not be 1. C, all right? C, okay. Because e to the 6x is, again. And then the plus 2x is plus 0, okay? Okay. Looks like you multiply both sides of the equation. No. Well, it's 1 minus c, c minus 1 minus c. It disappears. You don't really want to do that. The last equation gives c is equal to minus 1. I'm not real certain of that, but let me see if it does. Let's pretend that goes away. And you got 3 plus, 3c is equal to 0, So 3c is equal to minus 3, c is equal to minus 1. It doesn't seem fair to do that because you just threw away a c there in the denominator, but it does come out to minus 1. So your final answer is this thing, okay? That thing, okay, there it is. Y is equal to 3 times 1 plus, 1 minus, okay, down here. 3 times 1 minus e to the 6x over 1 plus e to the 6x plus 2x. That, I think, is your final answer. Plugging in a minus 1 there. And that, I think, is what they got. 3 times 2x, they put the 2x in front. 3 times 1 minus 6x over 1 plus e to the 6x. Okay. Now, they said, with the aid of a graphing utility, thank you very much, shows the graph of the particular solution. This is the whole family of solutions. All of you have books? You don't yet, so it's going to be hard to find a place to do. But here it is. This is the whole family of the solution. The one where c is equal to minus 1 is that blue one. Okay? As two slant asymptotes appears and does some other stuff with that. So, rather bizarre looking graph, but your graphing calculators will probably do it okay too. So that finally finishes 2.5. Homework exercises. Do any of the odds 1 through 9. And by the way, they mentioned each differential equation in 1 through 14 is homogeneous. And if you look at that, sure enough, the order of the number 1 is 1, 1, and 1. Number 3 is 1, 1, and 1. Number 4 is 2, 2, and 2. Number 6 is 2, 2, and 2. Number 7 is 1, 1, 1, 1. Yeah. All those look like. So any of the odds 1 through 9. And then either 11 or 13 or both. Now, how do they say that 13 is homogeneous when you have an exponential function in there? I'm not sure I buy that. I say everything up till there. 11 is homogeneous because the degree is 3 in every term. 12 is homogeneous because the degree is 2 in every term. 14 even. No, 14 has logs in it. I think they meant 1 through 12. I don't think 13 and 14 are homogeneous. Okay? But try to do 11 or 13 or both. Then do any of the odds 15 to 21. No, I'm sorry. 15 to 19, and they say those are all Bernoulli equations. Okay? 21, try to do 21. They say that's a Bernoulli equation. Let's see if that seems to be the case. Yeah, that would be a Bernoulli equation. Okay? Do any of the odds 23 to 27. Okay? And then do 29. Now the discussion problems, not a bad idea to look at those, but I wouldn't get too bogged down with them. Okay? However, in looking at them, look at number 35. Here's a differential equation known as Riccati's equation. Sounds like a pasta, doesn't it? But it's really not, okay? Who was Riccati? You know, I think this is the first time I've run across him. So that would be a good paper topic. Or, how did he develop this equation? Or, what in the world do you use a Riccati equation for? What are some applications of that? So you have 3 possible paper topics right there. There's another one down there on population growth under math models called the logistic equation. Now, that's not named after somebody, but I promise you, logistic equations are used in populations. They're used in disease transfer. My wife is an epidemiologist. She uses logistic regression to study diseases because they follow logistic equations. When you start out an infection in a population, usually the rate is very slow, and then it goes very high, and then it tapers off because everybody's been infected. So you follow that S kind of curve. Same thing happens to population growth. Because what are you talking about? You're talking about population of microorganisms. Okay? That's what leads to diseases. Okay. So the next thing we'll do is 2.6. And unfortunately, the sad time has come, hasn't it? That we are through. So we'll begin 2.6 next time. And hopefully it won't go quite as slowly as this one did. Okay? I don't know. I think I have it to keep. Oh, okay. We should have done that ahead of time.
5,
yeah.
It adds the slope of the tangent line to y prime.
That is y prime.
So I need to plug that into that or take the derivative of that because it's talking about the slope of the graph of this.
Oh, wait. Let me just check that and make sure. Let me see if I can remember where I got that problem. Oh, chapter 1. Which problem is that? 5. No, okay. Okay. Let me read the problem again. The graph of a solution of that. This is your difference of way to dy dx is equal to this thing. Okay. Now, yeah, I think this. Now that really has to just plug in this y and that x there. That's what it looks like now.
So when I plugged it in, I was getting right. As you plug in.
No. Okay. Is that for him and me?
Yes, that's for him.
Yeah, okay. He's right back there, Richard, I think. Is he in there? He was earlier. Okay. All right. Okay, let me end this now.